How's it going, everybody? I wanted to cover a quick video regarding the most common things that I see people asking questions about when it comes to BGP. Control plane, data plane, and best path selection. Now, there's a couple different ways that you can look at BGP, and I want to talk a little bit about how the specifics come into play. First one I want to talk about is going to be iBGP. What does iBGP mean? iBGP means that you are peering with other routers inside of your own autonomous system number. Well, hold on. What's an autonomous system? An autonomous system, essentially, if you were to Wikipedia this up, and I didn't actually do that, essentially means routers under your control. That's what that means. So if you own an autonomous system, so you've gone out to the governing bodies like ARIN and things like that, and you've paid some money to them and you've provided justification, you can go ahead and get your own autonomous system number. And it's going to be a public range. For those organizations that don't do that and they still want to peer via BGP, they can typically use a private ASN. So you can go talk to your provider, say, hey, I want to do this. This is how I want to do it. They're going to say, cool. And then they'll say, hey, use this autonomous system number to peer with us. That's an eBGP peering, though. So I want to be clear on that. So an iBGP peering comes in two different styles, two common styles. The first one is going to be a full mesh. What does a full mesh mean? A full mesh means that you are peering everybody to everybody else. That's what this means, like this. Everybody's talking to everybody else. Now imagine 1,000 routers and they're all part of the same autonomous system, and then you go on to say R7 and you have to peer with 999 other routers. That's a lot of work. So a way to combat that is to use route reflection. What is route reflection? Route reflection is the idea of you have your own autonomous system number, right? And then you go on R1 and R2. These will be your route reflector clients. They will peer with R5. R5 will peer with R1 and R2. R5's configuration will tell that R1 and R2 are route reflector clients, meaning that if R1, for example, decides to advertise any route or learns any routes in this way, R1 will take that route and propagate it to R5. R5 will then propagate it down to R2. He'll learn about it. And the same thing with R7 to R2. He learns a route in, he will go ahead and propagate it to R5. R5 will send that down to R1, and everybody will be happy. That is essentially what route reflection's job is to do. It's try to minimize the control plane in the iBGP design. So that's essentially what you would want to do. Now we've talked a little bit about how this comes into play with iBGP, and we've got everything connectivity-wise in place. Now, what happens if you want to propagate routes or you want to learn about routes from other people? Well, the simple fact is the control plane alone, when you do this, when you are looking at how this comes into play, when you do the control plane peering, this alone doesn't advertise routes, right? All you're doing is forming a BGP peering. So what I want to do instead is I want to go, assuming that you've learned routes, like R1 knows how to get them, whether it's through OSPF or RIP or whatever mechanism you want to do, as long as R1 or the router that is going to be doing eBGP connectivity has those routes in its routing table. That's the first caveat. R1 has to know about the routes. They have to either be connected to the router itself, or they have to be learned through the routing table, which means they're a best route through some other IGP's best path selection algorithm, or shortest path first, or dual Bellman forward, whatever the mechanism that you're using. You have to be able to get the route into the routing table. Once you check that box, you can go ahead and use the network statement. The network statement is going to allow BGP to propagate the route. That is when you start getting into the data plane, because then you're now actually forwarding traffic. You're advertising routes that can be reachable via other peerings. So you do that on all sides, right? You use the network statement over here to advertise whatever routes are going on. Now, another way to do this is with redistribution. Now, the reason why redistribution comes into play is because if let's say I've got 1,000 subnets over here on this box, let's say there's 1,000 over here. On a per box basis, I would have to advertise between R1 and R2. I'd have to advertise, that's going to be 1,000 and 1,000, that's 2,000. I'd have to advertise 2,000 network statements on both R1 and R2. That's just not feasible. Most people aren't going to do that. So to remedy that, what we end up doing is we come over here to RIP. In this case here it's RIP because I'm just having a little bit of fun with my lab. We would go underneath BGP and we say redistribute RIP, and then we would match on those routes that we want to advertise. Redistribution allows me to take any route that's in the routing table that matches whatever I define. If it's just a normal redistribution statement, it's going to grab everything. I can be more specific with prefix lists attached to route maps for specific propagation. But what that allows me to do is redistribute those routes into BGP, and they get propagated outbound. So, and then everybody sees everybody else's routes. So that's how the control plane comes into play, and that's how you begin leveraging the data plane. So the problem with that, though, is when I get propagation in place, I'm going to have routes going out this way, it's going to go out this way, and remember we have this full mesh of peerings out here on the internet doing its thing, and then I got a full bunch of routes coming in this way, then I have all these routes from over here are being learned over here. So not a bad thing necessarily, right? The reachability is in place. Now, the drawback to it is you can get into some routing issues if you're not careful. So what you want to do is you want to be able to take advantage of the best path selection algorithm. And what that basically does is it allows on a per autonomous system basis, on a per peering basis, and some other variations that come into play, how to control that. The first one that we typically are going to see is how we direct traffic from inside of our network out. So we've learned a route inbound from somebody we're peering with. It could be the default route, it could be a provider-owned address space, or it could be the entire routing table. It could be any one of those three variations. Let's say, for example, it's just a default route, and we want R1 to be the preferred exit path inside the network. So what we can do is we can go underneath this peering here to R6 and say, hey, whatever route I'm learning from you, and you're not telling R6 this, you're telling R1 this, and it's going to propagate to the other routers. If I'm learning a route in from R6, I want to go ahead and set the local preference to be, say, 200. The higher the better. That's one of the caveats. And then what's going to end up happening is that's going to get propagated to R5. R5 is going to propagate that into R2. And R2 is going to learn that to know to point to R1 for its routing. Now, that's all well and great. You don't have to do it for everything. In most common terms, you're going to do it just for specific routes, like the default route, internet connectivity, things like that. So that's great and all, right? But we're still advertising all these routes here outbound. How do I make sure that R1 is preferred for both outbound traffic, so with local preference, and inbound traffic? Well, the fact of the matter is that you would end up getting routes both ways, depending on how routing figures itself out. You could bring traffic in both ways because you're advertising the same subnets from both peerings. R10 and R11 are going to know how to reach them from both. Now, what's going to end up happening is you can come in on this side over here and you can make R1 your preferred exit path. And this is typically what I work with when I'm talking to customers. This is what they want to do. They want to pin traffic inbound and outbound to a particular peering. Cool. So what we can do is we can say AS path prepending. What a prepend means is you're going to add AS 100. You're going to add more AS hops in the AS path. It's a figure of speech, if you will. So instead of it being 100 here, then 200 here, and then 300 here, and then your AS path, let's say, for example, we've got 3.3.3.3/32, his AS path will be 200 and then 100. Why will it be that? Actually, this will be over here. It'll be left, it'll be network statement, and then next hop, and then the AS path list, and then how it was advertised. So that's essentially what it's going to look like. So what our goal is to do is we're supposed to come over here on R2, setting outbound. We're going to say, I want to add in 100 two more times. So that it makes this path right here less preferred. I do not want to bring traffic in for anything going to AS path AS 100. I don't want to bring it in via router 2. I want to bring it in via router 1. So what it'll end up looking like through router 7, router 9, AS 200, and then eventually AS 300 is it'll look like this: 200, 100, 100, 100. And then you'll see 3.3.3.3/32. That's what you're going to end up seeing. So this path will be the R2 path. This will be the R1 path. So which path are you going to take? Well, obviously you're going to take the shortest AS path, and that is basically how that is going to come into play. If you guys have any more questions about anything when it comes to this, please leave a comment in the comment section below, and I'll catch all of you folks in the next video.